All right, so we're in section 7.4 now. We're talking about integration of rational functions using something called partial fractions. Now, partial fractions is something that you have most likely talked about before. It's a topic we usually cover in a pre-calculus or a college algebra type of course. But it's not something you would have used in Calculus 1. Its purpose for showing up in a pre-calculus class is actually to give us the tools to do what we're doing here in Calculus 2. So just a quick little bit of background. So again, the types of functions we're dealing with here are rational functions. And if you recall, a rational function is a polynomial divided by some other polynomial. Now, we haven't, this isn't brand new territory for us. We have integrated rational functions before, but they've only been specific types. So for example, any function that has this form to it. So 1 over some linear polynomial. That means a polynomial of degree 1. Remember, the degree of a polynomial is the highest exponent on your variable. So any function of this form, 1 over ax plus b dx, if we integrate that, will always come out to this, 1 over a times the natural log of the absolute value of ax plus b plus c. And this is easy to come up with using a u substitution. We would just set u equal to ax plus b, and then this is what the end result would be. Another type of rational function that we've been able to integrate are functions of this type, 1 over x squared plus a squared. And really any any function that looks like 1 over x squared plus some constant can be thought of as being in this form, some positive constant specifically. We know with, again, you can use a u substitution to show that this will integrate out to 1 over a times the inverse tangent of x over a plus c. And, you know, I'll leave it to you to show this, but you should have seen this before. In the case where a is equal to 1, for example, 1 over x squared plus 1, that's just the inverse tangent of x. And you can see that putting 1 in for my a's here is just going to simplify that to the inverse tangent of x, plus c, of course, in both of these cases. Now, those are two specific types of integrals, or of rational functions, rather. But more generally, rational functions can look like any polynomial over any other polynomial. And this example here, x plus 5 over x squared plus x minus 2, how would I go about integrating that? Well, on its own, it's tricky. A u substitution by itself doesn't seem to work. It's hard to know what to choose for u here, but even if you choose the entire denominator as u, you don't quite get something that you can work out to x plus 5 up here. So we need to approach this in a slightly different way. Now, it turns out that this rational function can actually be written as a difference of two simpler rational functions. And I'll let you verify this, but this rational function here is the same thing as 2 over x minus 1 minus 1 over x plus 2. Now, if I converted my integrand here into this form, it's going to be a lot easier to integrate because both of these are basically this type of integral up here. So I can use, you know, a straightforward u substitution to find the antiderivative for each one of those terms, and I would get an answer pretty quickly. Okay, so the key in this section is figuring out how to take these relatively complex or relatively complicated rational functions and representing them as a sum or difference, or combination of the sum and a difference, of simpler rational functions that are more easy to integrate. The question, though, is how did I come up with this in the first place? How did I know that this could be written in this form? And the way that I know that is I can use something called partial fraction decomposition. So we're going to talk about what that means, how you perform a partial fraction decomposition on a rational function. I want to treat this in kind of a general sort of way. So let's assume that we have just any, rational function. And I'm going to write it in this form, p of x over q of x, where p of x and q of x are both just polynomials. That's what would make this a rational function. Okay. A common notation that we use when we study polynomials is this DEG, and then of p. What this means is the degree of that polynomial. So if this is a cubic polynomial, then the degree of p would equal 3. That's just an example. Okay. Now, we're going to look at how to perform a partial fraction decomposition by investigating 4 separate cases. But before we go to any of those cases, there's a process you always go through at the very beginning. The first thing you do is you compare the degree of the numerator polynomial to the degree of the denominator polynomial. If the degree of your numerator is greater than or equal to the degree of your denominator, so an example of that would be if both of these were quadratic polynomials, they would both have degree 2, so the degrees are equal. Or if p is something like x cubed, and q is something like, x plus 4 or something like that, the degree up here would be greater. In a case like that, you don't do the partial fraction decomposition yet. You start by doing long division on these polynomials. That's something else that you cover in an algebra class, how to do long division with polynomials. Our first example will walk through that. Once you've done that, if that was necessary, performing long division on this will produce something that looks like this. S of x plus r of x over q of x, where all of these s and r and q are polynomials. This q is the same q that we have here. It would still be the same polynomial in the denominator. But doing that long division takes this quotient here and writes it as a polynomial plus another rational expression. But the rational expression that's left here is guaranteed to have a numerator whose degree is strictly less than the degree of your denominator. And that's really the place that we're trying to get this thing to. If that's not already the case, if the degree of p is not less than q, then we want to do division so that we end up with a quotient where that is true, where my numerator has a smaller degree than my denominator, okay? That r there we call the remainder term, or the remainder polynomial. We'll see how that works in our first example, okay? Once we've got it down to this form, or if we started with a rational function whose numerator had a smaller degree than the denominator, that's when we jump into these 4 different possible cases. Okay, so let's look at case 1. Case 1 is the case in which q of x, remember that's the denominator right here. Q of x can be factored as a product of distinct linear factors. What that means is that q of x can be factored into this form right here, where every thing in parentheses here is a linear polynomial, so the degree of each one is just 1, and all of them are different from each other. There's no repeated factors showing up in this case, okay? If you can do that, then it's always going to be possible to write that r of x over q of x that's showing up here in the following form up here. So that r of x over q of x, I can always write that in the form of a1 over my first linear factor that showed up on the previous page, plus a2 over that second linear factor, plus ... there's all these other factors that are showing up here, plus an over a(n)x plus bn. That's the last linear factor that showed up when I factored that q of x polynomial on the previous page. The a1s, the a1, a2, all of these a's in the numerator, those are all constants. Okay, so that's the goal, is to take that rational function, write it in this form, and if you can do that, then integrating this is straightforward because we have a constant over a linear polynomial, which we saw at the very top of the first page how those things are integrated. So let's jump into an example where we can watch this process play out. Okay. I would like to integrate this rational expression right here. Now, if you notice, it's 2x cubed minus x squared minus 6x minus 7 in the numerator, x squared minus x minus 6 in the denominator. Before we jump into any partial fraction decomposition, which is what this thing is called right here, we need to first compare the degrees of our numerator and our denominator. In this case, the numerator has a higher degree than the denominator, and that's not what we want. So our partial fraction decomposition is not going to really work when we have that. we want to start by actually dividing these polynomials. Now, if it's been a while since you've seen this done, the way that we do long division with polynomials is your divisor, which is the thing in the denominator, is going to be written right here, x squared minus x minus 6, like that. And then my dividend, the thing in the numerator, is here, 2x cubed minus x squared minus 6x minus 7. Okay? So now what I do is I take a look at the first term in my dividend and compare it to the first term in my divisor. So I have a 2x cubed right here and an x squared right there. And I ask the question, what would I multiply this x squared by to get 2x cubed? And I can see that multiplying by 2x would do it. 2x times x squared is 2x cubed, okay? That gets written right here. Now that 2x doesn't just get multiplied to that first term. I used the first term to figure out what goes here, but after determining that, I have to multiply that 2x to all of the terms here. So for example, 2x times negative x would be negative 2x squared, and then 2x times negative 6 would be negative 12x. And now what I have is a cubic polynomial, which I'm going to subtract from these three terms that they appear directly below. Now remember, when you subtract polynomials, a way that's probably a little less error prone to do it in is to just treat it like addition, but change the signs of all of your terms. Okay, so if I wanted to subtract this minus the original polynomial I had here, that's the same thing as adding the opposite of that polynomial, which is what we're doing. 2x cubed minus 2x cubed is 0. If you're doing this correctly, these terms should always cancel out completely. Then I also have negative x squared plus 2x squared, which is x squared. I have negative 6x plus 12x, which is plus 6x. And then there's always this final step when you're doing long division where you take the next term that you haven't used yet from your dividend and you bring it down. So now I have a minus 7 there. Okay? I'm going to repeat this process a second time. So I compare the first term in this polynomial to the first term in my divisor, and I ask the question, what would I multiply this x squared by to get this x squared? Well, positive 1 would do it, right? 1 times x squared is x squared, so that's great. When I do that, 1 times x squared gives me the x squared that I wanted. 1 times negative x is negative x. 1 times negative 6 is negative 6. And then we do the same thing as before. We subtract this polynomial minus this one. But, like we said before, it's easier to just change the signs of that second polynomial and then think of it like addition. So again, these cancel. 6x plus x is 7x. Negative 7 plus 6 is minus 1. Now, if you notice, I've used all of my terms up here, right? And the degree of this remaining polynomial, which we call the remainder, is less than the degree of my divisor, which is what we wanted. What that does is it gives me this remainder term. So that 7x minus 1 is the new numerator that I'm dealing with. And then the divisor, x squared minus x minus 6, that's my denominator, okay? So I can rewrite this integral in this form. But so I can see that the first two terms will be very easy to integrate once I do that. But this second term here is still in a form that's tricky to integrate. So now what I'm going to do is I'm going to jump to case, I was about to say I'm going to jump to case 1, but I'm almost to that point. Looking at my denominator, 7x minus 1 over x squared minus x minus 6. I'm noticing that the denominator here can be factored. And remember, that's kind of what we're looking at for case 1. I want to see how q of x, which is my denominator polynomial, how does it factor? Well, it's going to factor down to x minus 3 times x plus 2. Hopefully you can see that pretty quickly. by now. You should be able to do that in your head pretty quickly. That's great. Case 1 tells me that if my denominator polynomial can factor down to something of this form, then I can write this rational expression in the form of a constant over one of those factors, x minus 3, for example, plus some other constant, potentially, over the other factor, okay? So that's what case 1 tells me will happen. This can be written in this form. The question is, what are the a and the b here? I need to know what these constants are, okay? Now, there are a couple of ways of determining these, and different instructors and different textbooks will tend to lean towards one strategy over the other. I have a strategy that I really like to use for determining A and B, and it may not be the one that the book tends to emphasize or a different instructor might emphasize, but this is just how I like to do it. So the first thing I'm going to do is I'm going to clear the denominators. Notice I have an equation here, and I'm going to multiply both sides by x minus 3 times x plus 2, because that would eliminate this denominator right here and leave me with 7x minus 1, okay? But if I did that on the right-hand side, multiply this by both of these terms, in my first term, the x minus 3 that I'm multiplying by will cancel with that x minus 3, but I'll still have an x plus 2. So the a in my numerator times x plus 2 is what I'm left with. Similarly, this b is going to be multiplied by this, but the x plus 2's will cancel, and now I'm going to be left with b times x minus 3. That's the only term that's left after the cancellation occurs, okay? Now, here's an important thing to keep in the back of your mind as you're doing this process. This is not an equation that we're trying to solve. More accurately, this is what we call an identity. So what that means is that the original functions, the original rational function on the left-hand side and the sum of rational functions on the right-hand side have to be equal to each other as functions. What that means is that this should equal this for any value that I plug into x, not just for certain specific values. So that's what we call an identity. When both sides are equal, no matter what you plug into your variable, okay? So the benefit of knowing that is that we can start plugging in convenient values for x on both sides of this equation in such a way that it makes it easy to solve for a and b. So for example, what would happen if I plugged x equals 3 into both sides of this equation right here? Well, on my left-hand side, I'd have 7 times 3, which is 21, minus 1, which is 20. On my right-hand side, I would have 3 plus 2, which is 5, times a, which I prefer to write as just 5a. But over here, when I plug a 3 in for that x, 3 minus 3 is 0. This whole term goes to 0. That's the reason I chose the 3 in the first place, because here I have an equation with two unknowns, a and b. I want to get rid of one of those so that I can solve for the other. And by plugging a 3 in for x, I've gotten rid of the term that involves the b. So now I have this, 20 equals 5a. If I divide both sides by 5, I can see that a is equal to 4, okay? Let's do that again, but let's plug something different in for my x. If I plug a negative 2 in for x, like this, okay? Then what I am going to see on the left-hand side, 7 times negative 2 is negative 14, minus 1, that's negative 15. And then over here, if I plug negative 2 in here, this term will go to 0, which is why I chose negative 2 in the first place. This side is going to become b times negative 2 minus 3, which is negative 5. So I get negative 5b from that. Solving for that, b comes out to 3. Okay? What did all this tell me? Well, that tells me that for my a and my b here, I have actual constants that I can use for the numerators. And that means I can rewrite this entire rational expression as a sum of two rational expressions that are easy to integrate. So now we're going to the actual integration step. If I want to integrate this rational expression right here, this rational function, I'm going to rewrite it in this form, 2x plus 1 plus, remember we had this remainder here which produced another rational function, but I'm going to write that rational function in this form. So plus 4 over x minus 3. That's what a was, right? A was 4. Plus b, which is 3. So I'm going to say plus 3 over x plus 2 dx. And integrating this is straightforward because I know what the 2x becomes. It becomes x squared. 1 becomes x. Here, remember, we're looking at these types. We're looking at these types of integrals now. Now, I see that there's a 1 in my numerator here, but even though that 4 is not a 1, if I were to integrate just this term, that 4 can be brought out of the integral so that I do end up with a 1 there. So a different constant up here is easy to deal with. But this would come out to plus 4, because that's what would come out of the integral, times the natural log of the absolute value of x minus 3, because that's how the u substitution would work out when I do that, plus that 3 right there, times the natural log of the absolute value of x plus 2, and then of course we have to have that plus c in there. And this is my final answer. And if I really, really wanted to, I could use some logarithm properties to maybe, like, you know, combine some of this stuff. I don't care about that for this problem. I'm going to leave that alone. Okay, but so now we've done one problem where we needed partial fraction decompositions. And as we've seen, the idea, again, I keep reiterating this, is to reduce this kind of complicated looking rational expression into a sum of easier to manage terms, which you can then just integrate directly. So starting in the next video, we're going to look at some of the other cases that we might come across.